So let's look at Bibo stability in some detail. Okay. Any questions on the examples and the general conclusions which I drew from them? So I am going to prove one of them. Okay. So that is my intention now. Yes. Okay. Any questions? Anything? No. Okay. So let's look at Bibo stability, right? So we know that y of s is p of s times u of s, right? So you give me any plant transfer function, the output to an input u is going to be p of s times u of s. This implies that y of t is going to be equal to 0 to t p t minus tau u tau d tau, right? So I am using the convolution integral. Okay. So let the magnitude of u of t be bounded by a positive real scalar m for all t greater than or equal to 0, right? Correct? Okay. Then what will happen? The magnitude of y of t is equal to the magnitude of the integral 0 to t p t minus tau u tau d tau. This is going to be first of all less than or equal to integral 0 to t the magnitude of p of tau magnitude of u of tau d tau. Do you agree? How did I get this? It's a property of the integral, right? So just to give an analogy, if you have, let's say, two scalars a and b, and you add a plus b, right? Let's say a and b are real numbers, right? So a plus b, the magnitude of a plus b is going to be less than or equal to the magnitude of a plus magnitude of b, what we call as triangle inequality, right? So a similar thing, right? So because if you have an integral and you have the integrand, first on the left hand side I am taking the absolute value of the entire integral, right? And that's going to be less than or equal to the integral of the absolute value of the integrand. Okay, so that's what we are doing, right? Okay. Now this is going to be less than or equal to m times integral 0 to t the magnitude of p t minus tau d tau. Do you agree? Yes? Yeah, m is greater than 0, right? Sorry? Yeah, this is a magnitude, right? So yeah, so it was there in the slide, so that's why I didn't. Let me write it down. Okay, here m is a finite positive real number. Anyway, I'm taking taking the absolute value, right? So absolute value of u of t, right? So it's going to be a positive number, right? So yeah, okay. So I hope it's clear. So now, please remember, what was p of t? It was what is called as the impulse response function, right? If you recall the physical meaning of p of t, right? So, question becomes, the question that we would ask ourselves is that when would the magnitude of y of t be bounded? Given this expression. So given this expression, when do you think the magnitude of y of t will be bounded? See, the magnitude of y of t is bounded by this integral, right? M times integral 0 to t magnitude of p t minus tau d tau. Now, suppose let's say this integral is bounded. Right? Certainly the magnitude of y of t is bounded. Don't you agree? See, because magnitude of y of t is less than or equal to m times integral of 0 to t p t minus tau d tau. Okay? So the follow-up question that we would ask is that when is integral 0 to t magnitude of P of t minus tau d tau bounded. Correct? Isn't it? So, when do you think the integral of a non-negative integrand would be bounded? Why am I saying non-negative integrand? Because I am taking the absolute value of P of t minus tau, right? So, P of t minus tau anyway can be a real valued function, right? It can take positive or negative values, but then once I take the absolute value, it's going to be non-negative. Why am I saying non-negative? It can be greater than 0 or equal to 0 also, right? So, P of t minus tau, the absolute value of it is going to be a non-negative function. So, I am taking the integral of a non-negative integrand. When do you think this integral will be bounded? Only when limit t tending to infinity, magnitude of P of t is equal to 0. See, otherwise, like if this limit doesn't go to 0, see, integration is like sum, right? If P of t doesn't go to 0, right? What happens if you keep on integrating? The number is only going to increase, right? So, for example, let me just give you a simple illustration, right? Because magnitude of P of t, let's plot it, okay? So, let's say magnitude of P of t goes something like this, and then like it settles down to a non-negative value. What's going to happen? Integral is just the area, right? So, what will happen is t, although the magnitude of P of t is bounded, the integral is going to become unbounded as t tends to infinity. What is the only scenario when the integral will be bounded, when the area will be bounded? Only when the function itself goes to 0 as t tends to infinity, right? So, this is the condition. So, we can immediately see that this implies that magnitude of y of t is bounded for all time if limit t tending to infinity P of t is equal to 0. Okay, so this is a sufficient condition for Bibo stability, right? It says that, look, you give me the impulse response, okay, and if the impulse response decays to 0 as time t tends to infinity, then my system is Bibo stable, okay. But then, okay, this is a good concept, but still we are not there, right? So, because if I want to test a system using impulse response, we know the difficulty that we would face, right? Because it's very difficult to generate an ideal impulse, right? So, then how do I get the impulse response? How do I test the system for its stability? Okay, so that's going to be a question, right? So, now can there be an equivalent criteria for this? Yes, there is, and it's based on poles. Okay, so that's what we are going to look at. Okay, so let's see, like how we get an equivalent criteria. Okay, we are only done with half the derivation, right? I hope it's clear till this point, right? We want to figure out when the system will be Bibo stable for a bounded input, right? For any bounded input, when will the output be bounded? We figure out that the output is bounded if the the limit of the magnitude of the impulse response goes to 0 as t tends to infinity. Okay, now let's go further, right? Okay, we already know that P of s is going to be equal to n of s divided by d of s, right? This is the Planck transfer function, right? And the Laplace of P of t is going to be equal to P of s. This is also something which we know, right? So, let there be k distinct poles of P of s, okay. Let the multiplicity of the pole Si, okay, Si, I going from 1 through k, be mu I, okay. So, okay, the system order is n, okay. So the order of the system is anyway n, right? That is a general notation anyway we are following, right? The order of system is n. So this implies that there are going to be n poles, right, of the transfer function. That's something which we already know, right? We are dealing with a generic case, nth order system. Okay. So let us say out of these n poles, let k be distinct. Okay, I am doing a generic case. Okay, of course all n can be distinct. That's also okay, right? So in a few examples we would have seen that, you know, like the poles were distinct. There are no repeating poles, but there can be repeating poles also, right? We are just doing the generic case. I am saying, like, let there be k distinct poles, k being less than or equal to n, right? Okay, and let the multiplicity of the pole, okay, I missed the word pole, okay, Si be mu I. Okay, what is meant by multiplicity? The number of times it repeats. Okay, if it is non-repeating, multiplicity is 1. So this implies that summation I going from 1 to k mu I should be equal to n, right? Correct? Let's say if I have a 10th order system, and let's say, you know, like I have 9 non-repeating poles with the 9th pole repeating twice, right? Summation of the multiplicity should be 10, right? So that I cannot violate, right? Fine. So essentially the summation of the multiplicity should be equal to the order of the system, which is the total number of poles. Correct? Okay. Now immediately we see that P of t, which is the Laplace inverse of P of s, can be written in this particular form. Okay. So it is going to be the n of s divided by s plus okay, let me see how I can change the notation. Okay, that's okay. S plus si s plus s1 whole to the power mu I, s plus s2, sorry, mu 1, right, s plus s2 mu 2, right, all the way till s plus s2 s k, okay, to the power mu k, right. So that's how this is going to come up, right. So that's how I can split the denominator polynomial, right. I can factorize the denominator polynomial. Now I need to take the LCM, right. Now how can I write the LCM? I need to take the partial fraction expansion, right. How would the partial fraction expansion look in general? We did a few examples last time, right. So if you had a what to say, the if you had a repeating pole, what did we do? Let's say if we had a factor like 1 by s plus 1 whole square, what did we do? We did like a by s plus 1 plus b by s plus 1 whole square, right. So you will have two terms, isn't it? So what is going to happen is that if when we do the partial fraction expansion, we are going to get something like this. Let's say, let me call it as L going from 1 to k, M going from 0 to mu L minus 1, okay, some CLM, which is the residue, right, divided by, okay, s plus s1 to the power, sorry, s plus sl to the power m plus 1, okay. That's what is going to happen. Okay, because what is going to happen, you know, like let me give you an example as an aside. So for example, I hope I did it correctly. Let's double check. Okay, see, for example, let us say I have a system where whose transfer function is this, all right, 1 by s plus 1 plus s plus 2 plus times s plus 3 whole square, right. What is the order of the system? What do you think is the order of the system? See, the order of the system is the order of the denominator polynomial of the transfer function, right. What is the order of the denominator polynomial? 4. So n is going to be equal to 4, right. And what are the poles? It's going to be minus 1, minus 2, minus 3 and minus 3, right? There are 4 poles, but minus 3 repeats twice. So what is the number of unique non-repeating poles? K? 3. So then what are the values of mu1, mu2 and mu3, which are the multiplicities of the 3 non-repeating poles? Mu1 is going to be 1, which corresponds to minus 1. Mu2 is 1, which also corresponds to minus 2, and mu3 is going to be 2. If you add mu1 and mu2 and mu3, what do you get? You get 4, which is n, right? Now, if you want to do the partial fraction expansion, what will we do? We will write a by s plus 1 plus b by s plus 2 plus c by s plus 3 plus d by s plus 3 whole square, isn't it? That's what we would do, right? That's the same thing I have done in compact form, right, using the summation. So I have essentially 3 unique poles, non-repeating poles, and each pole I am summing inside once again, right, because there can be multiplicities, right? So that's what I am doing here, right? So essentially what we have done here is that a by s plus 1 plus b by s plus 2 plus the c, I can take it as m is equal to 0 to 1, right? Some c 3m divided by s plus 3 whole to the power m plus 1. Okay, that's what I have done. Okay, if you expand, that's what you will get, right? You will get 2 terms, right? That's what we have done. So the CLM are the residues. Okay, I am just putting 2 indices because I have 2 summations, right? That's it. What I called as A, B, C, D, I am just calling as C subscript LM. Okay, that's just the change in the notation. Okay, because I have 2 indices L and M. I hope it's clear how we got it, right? Yeah.
P of S is ns by ds, right?
I am sorry, P of S? Ns by ds.
Why is P of t equal to ns by ds?
Oh, I'm sorry. Thank you. Okay, I'm still in the complex domain. Thank you. Oh, please erase that. I'm sorry about that. Okay, this is P of S. Okay, we have not taken the inverse Laplace transform yet. I meant to write it separately, but I think I just continued with it, right? So now we are going to come there, right? So now comes P of t equals Laplace inverse of P of S, right? Is it clear? Now we take the Laplace inverse. So now in this particular problem, if I take Laplace inverse, like what will I get? Let's continue with this problem, right? If I take P of t, I'm going to get a e power minus t plus b e power minus 2t, right, plus c e power minus 3t. Then what is the Laplace of 1 by s plus 3 whole square? t e power minus 3t, right? Once again we use the complex differentiation theorem. We saw this last week, right? So when we did the examples, right, that's going to be t e power minus 3t. So now I'm going to generalize from here, right? So this implies that P of t is going to be equal to summation L equals 1 to k, summation m equals 0 to mu L minus 1, CLM, right, e power s, sorry, t power m, right, e power SLT. Okay, I have just generalized from that. Okay, because you see that when there is no multiplicity, there is no t term. Okay, because anyway you won't have the summation with respect to m. You will have a summation with respect to m only if you have multiplicity greater than 1, 2 and above, right? So then you will have t power m. So for m equals 0, which is the case when you don't have any multiplicity. See, for example, for the pole at minus 1, what is mu1? It is 1. So what does it mean to say m equals summation m equals 0 to 0? You just use m equals 0, that's it, right? So you won't get a t power term at all. Do you agree? Yeah. So, but then like for any case where the multiplicity is 2 and above, you would get a corresponding t term, right? So that's what we are going to have. Do you agree? Is everyone what to say in agreement with what I have written? I am just parallelly doing an example and then doing the general case so that we can map them. Okay? Yeah. Now, once I get this, so this means that the magnitude of P of t is going to be equal to the magnitude of summation L going from 1 to k, m going from 0 to mu L minus 1, CLM t power m e power SLT. Once again we use triangle inequality, right? So the absolute value of sum of numbers is going to be less than or equal to the sum of the individual absolute values, right? So what will I have? I'll have this. Okay, do you agree? That's what we'll have. Right? Okay. Now, like let's look at this further. Okay, S power L is going to be equal to sigma L plus j omega L. Okay, because in general you can have the poles to be complex conjugates. Okay, I am taking the Lth pole. Okay, which is sigma L plus j omega L. If it's real, j omega L term is not there. Okay, so what will be e power SLT? It's going to be equal to e power sigma L plus j omega L times t. This is going to be equal to e power sigma LT e power j omega LT, right? Because e power a plus b is going to be equal to e power a times e power b, right? So that's what we have. Now what can you say about the magnitude of e power SLT? That's going to be only magnitude of e power sigma LT. Why? Because e power j omega LT magnitude is 1, right? And e power sigma LT magnitude is anyway e power sigma LT, right? Because anyway the exponential term is non-negative, right? It can asymptotically go to 0, but it's so I just remove the absolute sign. Is it clear how we got this simplification, right? So we are almost there. Okay, of course this was a long derivation, right? So see, by and large I think this is the only proof I am going to do. Okay, so in future we will make use of results, right? That's going to be the focus for this particular course, but at least I wanted to show you, okay, so that you understand how the inner details of whatever we are learning works, right? So essentially this shows that the magnitude of P of t is going to be equal to summation L going from 1 to k, m going from 0 to mu L minus 1, magnitude of CLM. Anyway, t power m I can just write it as it is, because anyway we are only taking the case t greater than or equal to 0. I can just write t power m, and then this we got as e power sigma LT. Do you agree? Now, if sigma L is strictly less than 0 for all L going from 1 to k, what can you say about the magnitude of P of t as t tends to infinity? It will go to 0, right? Because please see that, please note that the left hand side is less than or equal to the right hand side. In the limit t tending to infinity, if the right hand side goes to 0, obviously the left hand side has to go to 0, because the left hand side cannot take negative values, right? Magnitude of P of t is non-negative. Okay, so the only choice for that is that like magnitude of P of t should go to 0. Okay, so this implies that limit t tending to infinity, the magnitude of P of t goes to 0. Now immediately one may ask the question, hey, what about the t power m term? right? It so happens that the exponential term with the negative exponent will dominate the t power m term. Okay, so the product will go to 0 anyway, right? So it so turns out that, you know, like the sufficient condition for the impulse response to asymptotically go to 0 is that I need to have all poles to have negative real parts. Okay, let's say there are k distinct poles, k can be less than or equal to n, right? So whatever poles are there, all poles must have negative real parts. Okay, or in other words, we should have all poles lying in the left of complex plane. Okay, yeah. Yes please.
Can we take that magnitude of e power xlt is nothing but magnitude of e power sigma and
Okay, so okay, let me I just skipped one step there. Okay, so shall I write here? So if I take magnitude of s power lt, it's going to be equal to magnitude of e power sigma lt e power j omega lt, right? So this is going to be magnitude of a times b, this is going to be magnitude of a times magnitude of b, right? So e power sigma lt e power j omega lt, right? And what is e power j omega lt? If I use Euler's relationship, it's going to be cos omega lt plus j sine omega lt, right? Now if I have to take the magnitude of this complex exponential, what do? Real squared plus imaginary squared, square root. What is cos squared plus sine squared? 1. If I take the square root, I will get 1. That's why it vanishes, right? It becomes 1. Is it clear? Okay, good point. Okay, I just skipped it. I hope it's clear to everyone now, right? Yeah. So to summarize, we see that this implies that if all poles of the Planck transfer function lie in the LHP, okay, that is have negative real parts, okay, then the system is Bibo stable. Okay, some people will say it's asymptotically stable. Okay, we are going to shortly see what that is. Okay, so that's what it is. Okay, so the important condition here is that, like, I find the system transfer function, and if all the poles of the system transfer function have negative real parts, okay, that is even one what to say, the so that is if all poles are in the left half of complex plane, left half of the imaginary axis, right, left of the imaginary axis in the S plane, then we have asymptotic stability, or what we call as Bibo stability. Okay, so is this also necessary? So what do I mean by necessary? You know, like, we have only shown what is called a sufficiency condition, right? So what we have shown, okay, if all poles lie in the left half plane, we have shown that system is Bibo stable. Now the opposite question arises: if a system has to be Bibo stable, do all poles need to lie in the left half complex plane? See, I hope all of us understand necessary condition, sufficient condition, and necessary and sufficient condition. See, if A is necessary for B to happen, right, that means that A needs to be true, okay, for B to happen. That need not imply that only A is required for B to happen, right? So if we say A is sufficient for B to happen, if A happens, that means that even B will happen, right? But then B can happen due to other reasons also, right? So we do not know, right? So essentially what we have shown is that we have only shown that the sufficient condition for Bibo stability is that all poles should lie in the left of complex plane. Now what is the other way around? Okay, that is, if a system what to say, is Bibo stable, then all the poles lie in the left of complex plane, right? Is that true, right? So is the what to say, the is the condition of all poles lying in the left of complex plane a necessary condition for Bibo stability? Why is necessary condition important? Only then we can talk about a corollary, right? Because if I say for Bibo stability all poles being in the left of complex plane is necessary, then I can say that even if one pole lies in the right of plane is unstable. With this statement I cannot show, right? Because let's look at this derivation, right? Now if you tell me I have a system where one pole is in the right of complex plane, what will happen to the what to say, this derivation? What conclusion can I draw from this derivation? Nothing. Why? Let's say one pole is in the right of complex plane, right? 1 sigma L is greater than 0. So what will that imply? I will only be able to conclude in the magnitude of P of t is less than or equal to infinity. That doesn't help me. That doesn't tell me it's unstable, right? Is it? See, 0 is also less than infinity. You know, like any other positive number is also less than or equal to infinity, right? Less than infinity, you know. So it really doesn't help me, right? So what we have shown is only sufficiency, okay? What about necessary condition? Okay, I leave it to you as homework, okay? It's not, once again, it's not necessary as far as this course is concerned, okay? But for those who are mathematically inclined, please go and look at the proof, okay? So it's available in many standard textbooks, okay, on controls. So I hope my point is clear, right? What we have shown is only sufficiency, okay? It so turns out that it's also a necessary condition, okay? So let me what to say, pose that question. Is this condition necessary? What do I mean by is this condition? All poles in LHP necessary for Bibo stability. The answer is yes. And that's why if we even have one pole lying in the RHP or on the imaginary axis, the system is not Bibo stable. Okay, that we have shown through examples, right? See, to disprove Bibo stability, I need to figure out only one bounded input for which the output is unbounded. We have already shown it, okay? Whether we call it critically stable, marginally stable, or whatever it is, but then we found that it violates Bibo stability definition. And if you have a pole in the right of plane, you give me any bounded input, the output will be unbounded. Okay, that is sure. If you give repeating poles on the imaginary axis, any bounded input will lead to unbounded output. If you have what are called like non-repeating poles on the imaginary axis, you can always find one bounded input for which the output will be unbounded, right? So that is why this is also how do we conclude? Because this is also necessary. See, I went from examples to a generic conclusion. The best way to do it is always to prove the generic one and then like do the examples, okay? But since this is a first course on controls, you know, like I wanted to do examples to motivate our understanding, and then like we did the general derivation, right? So this I leave it as homework, okay? The answer is yes. Okay, it is also necessary. That is why we are able to conclude that even if one pole lies in the right of plane, the system is not Bibo stable. Okay, and if we have non-repeating poles on the imaginary axis, once again, you know, like to me it's Bibo unstable, right? Because like I can always find one bounded input for which the system output is unbounded, right? So although many textbooks will call it as critically stable or marginally stable, that is because of another notion of stability. Okay, so what I will do is that maybe this is a good place to stop, okay, so that you can digest all this information, right?